Okay. Hey, one more. 40 minutes, or whatever it is, with me left. Okay, so we had question one figured out. I've written question one.
I did have an exam related question.
Yeah.
Would we be given a formula sheet or allowed to take it?
You're given a page note. You're allowed to take it to A4 double sided.
Okay.
I may give you a formula sheet, but no, I'll give you a formula sheet. No, the formulas are elementary. What else do I want to say? I'm going to include a summary sheet on the model, by the way, of every word I need to make sure you know about.
For example,
when we do spherical coordinates and stuff, can we just...
I'll give you the spherical coordinate thing.
okay, so we'll have
That's the coordinates.
okay, wonderful.
Can we just write down the...
Yeah, absolutely, absolutely. Yeah. Okay, we have question one sorted out on the exam. What's question two? What did we do in the second part of it?
Curl!
We did curl, we did what else?
Divergence!
Curl, we did divergence. This was more broadly under the umbrella of what?
Differentiation.
Differentiation theory. And we did also Hodge-star. Did we do anything else?
Curl, the divergence of the curl.
Yeah, so there are some key theorems to bear in mind there. We had the, let me rub this out now. So let's just remind ourselves, how do I write the curl as in terms of forms? So the curl of F is the vector field associated to what? Star D omega F. This is a what?
One form.
This is the one form. What's D omega F? Two form. Good. Okay, what was the divergence?
Star D, star.
Star D star omega F. Okay. So, does it make sense to say the following? If I look at the divergence of the curl.
Yes, but it's always zero.
It's always zero. How do I say this in words? A solenoidal vector field is incompressible. I'm not going to tell you what the words mean.
Solenoidal means
So if you don't know what incompressible means, that's going to be unfortunate.
incompressible means...
Yeah.
So let's just remind ourselves. Incompressible means the divergence vanishes.
Yeah.
Solenoidal means that it's written as what? The curl of another vector. Okay, how do we prove this thing? Plug it in. It's not even really a proof.
Couldn't we also do it directly?
You can do it directly, but it's not as enjoyable. You have to kind of do it coordinates. This is my approach is coordinate free. Okay, divergence. So just to do this calculation again.
That's D squared.
Hodge 1, D squared.
Divergence. That's the curl.
Hodge-star, but Hodge-star dies.
So star D star square D omega F. Star square is 1. So I get star D square omega F, but D square is
0.
D square is 0. What's the other manifestation of D square is equal to 0? Try again. A gradient field is irrotational. So d squared equals 0 in dimension 1 is d of df is 0, but that's exactly equivalent to gradient fields are irrotational. What does irrotational mean?
Curl of 0.
Curl is 0. And d squared equals 0 in dimension 2 is this thing here. This kind of a solenoidal vector field is incompressible. What what are methods of testing whether a vector field is a gradient field?
I can think of two off the top of my head. So there's Clairaut's theorem.
Clairaut's theorem, that's commutativity of partial derivatives. That gives you these theorems.
Well, you can test it on the py.
Oh, that initial thing I said about, yeah, okay, so that's what you're saying, that initial test of qx minus qy, and so on. Okay, what's the other one?
Just checking if the divergence.
You can just do it directly and things of that type. What's another way to do it? What's a kind of different way of testing it that we saw? Yeah.
If your domain is simply connected, you can see whether it's irrotational.
That's exactly right. What's a non-differentiation approach? Yeah. Take an integral over a closed curve. So, let's do it easy. So notice I'm saying here that a gradient field is irrotational. That's the one-dimensional statement of d squared being 0. But it's also equivalent to the line integral over a closed curve. Vanishing. What's the dimension of the curve? 1. So if it's path independent, namely this is true, which is kind of like a one-dimensional test. So you're testing the vector field on things of one dimension. If that's always 0, then it's a gradient field. So this is like a one-dimensional. What would the two-dimensional test be? It's the surface integral. So the two-dimensional integration test would be that the surface integral of f dot ds for a closed surface is 0. Would that give you a gradient field? What would it give you? Solenoidal. And this is surface independence. This is a surface independence property. Okay, what's an example of a closed surface?
Sphere.
Take a sphere. Good. That's what we do. Okay. The point I'm just trying to say here is that there is like we really did things in dimension 1 and then we did them in dimension 2. Yeah.
With these things, if you're trying to prove that it was a gradient field, just finding one closed loop that's 0 isn't sufficient.
Yeah, it's true for all closed loops. Yeah.
So this can only
Take the arctan one, for instance. If I do that over a small disk centered at a billion of radius 0.1, it's going to be 0.
So we can't actually prove it is a gradient field.
If it's true for all curves, then yes. And maybe you can deduce something about all curves from one curve or something. Okay. So what's the question I'm going to ask, given all this theory? What is question 2 of the exam? Say again? Start with a vector field. Good choice. So let F be some maybe R3 to R3, given by some formula. What's part 1? Say again? Well, I've already assessed the one form, I've already assessed the curl. Was that?
Is this question 3 or
Question 2 on the exam.
I thought question 2 is the divergence of curl and Hodge-star.
I need to make a question for it.
Oh.
What's the question I'm going to ask?
Is this vector field the curl of some other?
Okay. How would I write that statement?
Is it solenoidal?
That's how I would write it. I would write it like probably the following. Does there exist
If so, find J.
a one form, alpha, such that what?
D star df alpha equals.
What am I asking here? Can someone tell me that's not here? What am I asking here?
Such that d star d over.
So without the forms, what am I asking? What am I getting to? What am I writing in very convoluted language?
Is it a gradient?
No.
Is it a solenoid?
Is it a solenoidal vector field? How do I write that in a language of forms? I'm not going to use the div and curl, it's too easy. We're going to put it in a bunch of stars and D's, right? Does there exist an alpha such that omega f is equal to star d alpha? This is equivalent to asking whether it is a solenoidal vector field. Actually, this would be question 2. What would I ask in question 1? Compute what? I already assessed omega f. So if I'm asking you if it's a solenoid, what does it have to be first? Okay, so in dimension 1, if I'm going to ask you if the gradient field, what do I get you to do first?
Compute the
Get you to compute the curl first. So here I would get you to compute the divergence. So I would say compute, let's say, probably star omega f. Then, so this actually would end up being part 3, because then I would ask you to compute what? D star omega f. And then I would say from here, does there exist an alpha such that that's true? That's some way to have that.
So we've gone from 3 to 2. It's a very non-linear exam.
It is very nonlinear, yeah. Be prepared for that. Okay, so part 1 would be compute the Hodge-star of the associated one form, part 2 would be exterior derivative of that, part 3 would be to interpret some statement of forms in terms of kindergarten vector calculus. What would the next question be? I'd probably put some type of line integral thing in there, maybe a surface integral, just for enjoyment. So maybe part 4 would be a divergence theorem problem. Just to mix it up so you kind of see that all the subjects merging together. This doesn't mean I'm going to actually mimic this, but I'll probably mimic it very closely because I'm lazy.
In aid of your laziness, do you want to borrow one of our notes on this?
Your notes.
Because we've been taking notes.
I'm aware. Maybe I'm just tricking you because it's actually none of this is all. I'm kidding. I wouldn't do that. Maybe not. Well, you'll find out. Just have fun with it. Okay, question 3. What's question 3? I haven't done a line integral question yet, so what do I do with the line integral? If I give you a computer line integral. I'll probably give you the parameterization even, maybe. yeah, I could give you a line integral of a vector field. I could also then give you a line integral of a function, maybe. But usually I'd go structural better than this. But then if I'm going to do this, I'm definitely going to include a question like what? Not Stokes. Something about path independence, something about green slip, maybe. So I'd probably give you some curve. No self-intersection. Get you to compute the line integral of this. If it's a gradient field, that would require me to put a problem on gradient field. And then maybe a Green's theorem question. Green's theorem. Let's suppose, oh, here's a nice one I might put. I give you some region omega. I orient it this way. I then make it multiply connected, like this. What's the orientation of the boundary curves?
Oh, the other way.
Are they all the other way? They're all the other way. So I may get you to, I'll give you a multiple choice and it's a bunch of multiply connected domains and you figure out which one has the right orientation. Okay? So that's a nice one, and then I may get you to compute a, so that would be like 5 or something, or then I maybe get you to compute a double integral using Green's theorem over that. Okay? Yeah? What's the next question? We've got, that's 3 questions. What's next? We need to get into surfaces. So I've touched maybe a surface integral there, but probably not a hard one. So yeah, I definitely need to get a surface integral in there. What was that? On a torus, that probably is something I would like to do, yeah. So, question 4, I'd probably give you some...
But I don't know the parameterization of the torus.
Wait, who suggested a torus? Say a sphere.
Yeah,
Don't give him difficult ideas.
Please, anything but a torus.
Okay, so
It's not a torus.
maybe I'll give you this.
That's just a torus in disguise.
I get you maybe to compute a surface integral over a torus.
That's in the parameterization of the torus.
Maybe I need to figure out the parameterization. I'd probably give you the parameterization. But you would have to compute the cross product.
Fine, I don't care as long as I get the parameterization.
Okay, what else? What else would I do?
Nothing from chapter 5. You said that.
Oh, I actually wanted to show you guys something.
How is that a sphere?
I might give you one of these.
I'm only doing that to give you the parameterization. Otherwise I'm going right.
No, you bloody not.
This is what's called an Alexander Horn sphere. What you do is you take a torus, you slice it, you glue another torus in there, slice it again, and you do this iteratively. This gives you an example of a space where every irrotational vector field is a gradient field, but it's not simply connected. Interesting example. I've tried to draw it, but it's a bit complicated, so I'll probably have it ready by the exam. Don't worry, that's definitely not an example. That is definitely an example I want to show you guys. Okay. This is where I would probably be inspired to write questions.
There's no questions coming out of chapter 5. You said that.
Yeah, but I might use it as inspiration. So you can say, here's a torus. Here are some curves on a torus. Okay. So we're doing a surface integral. If I have a surface integral, I definitely need to talk about what?
Stokes theorem.
Stokes theorem. So I'll give you a Stokes problem. So I give you some type of surface integral. Maybe it's you know, given over some type of thing like this, and use Stokes' theorem to evaluate something like that. What would part 3 be, maybe?
Compute it a normal way and compare.
Say again, sir?
Compute the normal way and compare.
That's hard to do on an online one, because the answer is the same, so I can't verify necessarily that I've done the work. And the extent to which I know how to do that in terms of assessment is shaky at best. What's something I
mean,
could do?
couldn't we just do an exam where we just had work problems but scan it?
Yeah, but the logistics of doing that 200 times, and then getting that assessed 200 times, and then making sure nothing gets lost is,
Well, I mean, most maths courses did it.
Oh, you'd be surprised how bloody hard it is. You don't realise it until you
Cool.
start getting
That's a
It's
good
just,
notion.
you know, I think a lot of us are fairly justifiably concerned about the fact that if we make a numerical calculation
Yeah,
error,
yeah.
as you did in
Absolutely,
early in the
100%, and that's definitely something I'm going to make sure is taken into account.
That's one thing I have a lot of people from last year.
Yeah, so I would, if it was up to me, I would have you all sit in a room and do it by hand on paper. But that's not happening. Yeah.
So will we be able to show working, or is it just?
I'm
about
hoping that is the case. I'm 100% hoping that is the case. Again, this is the first course I've ever lectured. This is the first I've ever assessed. I have no idea how they do it. It's some wattle quiz. Yeah, I don't know. Okay, what's the next one going to be? What haven't we covered yet? Let's go back to the contents page.
divergence theorem.
Probably the divergence theorem would be the one I would go through.
Vector bundles.
I would put a vector bundle question on there. That's certainly the best. I want the divergence theorem. Here's I love my arctan example, so that's definitely going to appear somewhere probably. But I also like this example. I like this vector field.
I hate to be the bearer of bad news, but you said we needed to do 6 to 7 questions, and we've run out of content at 4.
Well, that's maybe we have to go into the high road for the last couple of questions.
You know what? Why not just rinse and repeat? Do some.
These are actually long questions, so I probably would split them out into 6 and 7.
Okay.
Let me write the vector field that I like, and I would make sure that you're comfortable with and familiar with to some extent. I let A be x squared plus y squared plus z squared to the 3 halves. Let f be x on a I hat plus y on a j hat plus z on a k hat. If you want your life a bit easier, make sure you can compute integrals of that thing, find that thing in the book. That's my recommendation. Just spend some time with this. What can you guess this is? Given that I like my arctan example. What does the arctan example illustrate? The path it's the distinction between something being irrotational but not a gradient.
Yeah.
What would this be? Not surface independent, even better. Well, yeah, on this string of things, what's the direct parallel? It'd be incompressible but not solenoidal. Make sure you know how to show that to varying extents. If I want to calculate the area, actually, let me just ask this. If I want to compute a surface integral, but it's too hard, what can I do and how do I do it?
Oh, you could either try and break it down into a line integral.
What theorem allows me to do that?
Green's theorem.
Not always. Green's theorem is a specific case of.
Or Stokes theorem.
Stokes theorem is for surfaces, Green's theorem is for regions in the plane. Okay, so I may want to convert it to a line integral. What if I don't want to do that?
Divergence theorem.
Try maybe the divergence theorem. If I already know that it's of some particular type, I can convert it to a triple integral using the divergence theorem. Usually you go to lower integrals, but we've seen that sometimes it's more efficient to compute a triple integral than to compute a surface integral. If I want to compute a line integral, but it's too complicated and I happen to know that it's irrotational, what can I do? I'll simply connect a domain. I can what?
Apply path independence.
Path independence, which would then allow me to just, if it's closed, it'll be zero, if it's not. Difference of the values of the potential at the endpoints. What else could what was something that was hard? Okay, I want to take the area of a region in the plane. And it's kind of complicated. How can I do it? Where does this appear in the notes? Not surface, just region of the plane.
Green's theorem.
How does Green's theorem get used?
You get the loop.
Yeah, you take the closed.
If I look at Green's theorem,
And then that's a closed loop.
if I look at this example, for instance, find the area of the ellipse. I parameterize the ellipse. And then apply Green's theorem to the function 1D should be the maker. An example to probably have in mind maybe. So example 4.2.3, that's something I would have. Okay, we've seen this. Have I missed anything?
Just a general statement. Please don't accidentally ask us to calculate the arc length. Oh, arc length. You haven't covered arc length.
No, I don't want to do that.
Okay, so we won't have to calculate the arc length of an ellipse or something called.
Yeah, which would require one theory or elliptic integrals of the first kind or something. What would I?
There's no close.
Oh, that's where that is.
Equations below.
Oh, would you be able to? I know this is a bit of an odd question. Would you be able to do something on conic sections?
I've done an example where we have a cylinder sliced out by of course that's not a conic section specifically, but it's still an elliptical region.
Yeah, you did do. Didn't you do a parameterization of cones?
Of cones, yeah, by spherical coordinates, yeah.
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 Oh, I just thought it would be a rather fun problem as you've got that connection to sort of ancient Greek mathematics, and there's an interesting theorem which relates, I think, curves of certain genuses.
Mm-hmm.
So I think
So you want a genus problem on that exam? You want maybe a Riemann surface of genus 3, and then we'll do some line integrals related to it.
oh no, of
You want to have a
sections.
torus.
So,
Torus is genus 1.
For example, all curves of degree 4 can be taken as a plane intersecting a torus.
Does everyone want that one?
No! Next time.
Okay. I think that I'm happy with that structure. Is everyone reasonably happy with that type of structure? Okay. Let's assume I follow something along those lines. Thank you for putting up with my lecturing for 5 weeks. think for the remaining 15 minutes, I'll just answer people's questions if you want to come up and ask. Okay? Do you want to ask me?
Will we get a formula sheet like?
Yeah, you'll get a formula sheet.
Okay.
You get a formula sheet and you get double-sided endpoint.
Okay.
Okay, when you say double-sided, do you mean two sides or do you mean a single
Two-sided
double-sided?
unequal A4. Euclidean paper.
What?
Damn it, you.
Euclidean paper.
Right, so you know, like,
Not projected paper.
so I can't back down a circle.
No, just flat. Euclidean paper.
I can't hang that.